Every physicist you have ever heard speak about death says the same thing. The second law of thermodynamics. Entropy always increases. Order falls apart. You are ordered, therefore you fall apart, therefore you die. The argument is clean, it sounds final, and it has an error in it. A two-word error. And those two words are the difference between death being a law of physics and death being an engineering problem. Now, let us start with what the second law actually says. The version that Rudolf Clausius formalized in 1865 when he first coined the word entropy. The version that Ludwig Boltzmann expressed as S equals K log W and spent the rest of his career defending, that version has a qualifier in it. And that qualifier does almost all of the work. The second law of thermodynamics says that in a closed system, the total entropy tends to increase over time. In a closed system. Most people hear entropy always increases and stop listening. They drop the first three words. And those first three words change the meaning of the entire sentence. A closed system is one where nothing gets in and nothing gets out. No energy crosses the boundary. No matter crosses the boundary. No information crosses the boundary. It is a box, sealed shut, left alone. And in a closed system, yes, everything runs down. Everything reaches equilibrium. A hot cup of coffee in a perfectly insulated room will cool off. The air in the room will warm up slightly. Eventually, the coffee and the air reach the same temperature, and nothing interesting ever happens again. That is the second law doing its work. The system has reached what physicists call thermal equilibrium, maximum entropy, maximum uniformity, minimum structure, and it stays there forever. That is what closed systems do. Now, if you were a sealed box of atoms with no energy source, then yes, you would reach equilibrium, you would run down, you would die. The second law would guarantee it, absolutely, unambiguously, without exception. But here is where the error creeps in. People hear entropy always increases and they forget the qualifier. They drop the words closed system. They take a law that applies to sealed boxes and they apply it to everything, everywhere, regardless of circumstance. And that is simply wrong. You are not a closed system. You are as far from a closed system as anything in the universe could possibly be. Right now, as you sit there listening to this, you are breathing. Air is entering your lungs. Oxygen is crossing your alveolar membranes into your blood. Carbon dioxide is crossing back out. You are metabolizing food that you ate hours ago, breaking molecular bonds, capturing the energy released, using that energy to drive thousands of simultaneous chemical reactions. Your heart is pumping blood through roughly 100,000 kilometers of blood vessels. Your skin is radiating infrared heat into the room at roughly the same rate as an incandescent light bulb. Energy and matter are flowing through you constantly, every second of every day. You are what physicists call an open system. And open systems play by fundamentally different rules than closed ones. An open system with a steady flow of energy through it can maintain order, and it can even increase order locally, as long as it exports enough disorder somewhere else. This is not a violation of the second law. This is perfectly consistent with the second law. The total entropy of the universe still goes up. But your personal entropy, the entropy right here, in this particular arrangement of atoms that you call your body, can stay low, or even decrease. No law broken. You just have to read the law carefully enough to notice the words closed system. Let me give you a mundane example. Your kitchen refrigerator. A refrigerator takes heat from the cold interior and pumps it out into the warm kitchen. That seems backwards, does it not? Cold things getting colder, warm things getting warmer. That seems like it should violate thermodynamics. But of course it does not. The refrigerator is plugged into the wall. Energy flows in from the power grid. The compressor runs. The refrigerant circulates. Entropy increases in the power plant, in the motor, in the warm air behind the fridge. But inside that cold box, order is maintained. The temperature stays low. The food stays fresh. Locally, entropy decreases. Globally, entropy still increases. No laws broken. The refrigerator is an open system, and open systems can do things that closed systems cannot. You are a refrigerator. I mean that with the deepest respect. You are a magnificently engineered, staggeringly complex refrigerator that has been running continuously since the moment you were conceived. You take in energy from your environment, food, oxygen, and you use that energy to maintain an extraordinarily intricate molecular structure against the constant, relentless pressure of thermal equilibrium. Every single day, your body repairs damaged DNA, replaces broken proteins, recycles worn-out cellular components, kills malfunctioning cells, rebuilds tissues, and manufactures new molecules from raw atomic materials. You do all of this with roughly 80 watts of continuous metabolic power, about the same as an incandescent light bulb. 80 watts to hold a human being together, to keep roughly 37 trillion cells organized and functional and alive every second for decades. So if the physics allows you to fight entropy, and you have been winning that fight since the day you were conceived, then why would the physics suddenly require you to stop? You see, there's an equation that seems to say exactly that. In 1825, a man named Benjamin Gompertz read a paper to the Royal Society in London. He was an actuary, a mathematician who calculated risk for insurance companies. The paper had one of those wonderfully long 19th century titles on the nature of the function expressive of the law of human mortality and on a new mode of determining the value of life contingencies. What was inside it was short and devastating. Gompertz had been analyzing mortality tables, records of how many people died at each age across large populations, and he found a pattern so clean, so consistent, that it looked like a law of nature. After roughly age 35, the human death rate increases exponentially with age. Not linearly, not a gentle, steady climb. Exponentially. Your probability of dying in any given year approximately doubles every 8 years. Let me make that concrete. At age 35, your annual risk of dying is roughly 1 in 1,000. By age 43, it has doubled to about 2 in 1,000. By 51, doubled again, 4 in 1,000. By 59, 8 in 1,000. By 67, 16 in 1,000. By 75, 32 in 1,000. The curve is relentless. It is exponential. And the equation that describes it is simple. Mu of t equals alpha times e to the power of beta times t. The force of mortality is an exponential function of age. The Greek letter beta, roughly 0.085 for humans, is called the Gompertz coefficient. It sets the pace at which death accelerates. Now, this might sound like a statistical curiosity, an interesting pattern in insurance data from 2 centuries ago. It is not. The Gompertz Law is one of the most robust empirical regularities in all of biology. It holds across countries, it holds across centuries, it holds across wars and famines and pandemics. Researchers have compared the Gompertz exponent across populations as different as India in 1900, Mexico in 1940, Sweden in 1949, and the United States across half a century. The absolute mortality rates were vastly different. Far more people died young in India in 1900 than in Sweden in 1949. But when you plot the logarithm of the death rate against age, the slopes are almost parallel. The rate at which mortality accelerates with age is nearly the same everywhere, in every era. And here is the data point that should stop you cold. In 1945, researchers compared the mortality of Australian prisoners in Japanese prisoner of war camps with the mortality of Australian civilians living in safety at the same time. The conditions could not have been more different. Starvation, disease, forced labor, brutality on one side, relative comfort and adequate nutrition on the other. The absolute mortality was vastly different. The prisoners died far more often at every age. But the Gompertz exponent, the rate at which mortality increased with age, was the same doubling time, the same exponential slope. Whether you were well fed in Sydney or starving in a camp in Burma, your probability of dying accelerated with age at precisely the same rate. Think about that. The Gompertz exponent is not about your environment, not your diet, not your stress, not your access to medicine. It is about something inside you, something intrinsic to how the machinery runs down. Now, If that exponent were a physical constant, like the speed of light or Planck's constant or the gravitational constant, then aging would be a law of nature, death would be physics. And you could not escape it any more than you can exceed the speed of light or violate the conservation of energy. But it is not a physical constant. We know this because there is a mammal that violates it. The most dramatic violation of the Gompertz Law is a small, wrinkled, mostly hairless rodent that lives in underground colonies in East Africa and looks, frankly, like something you would find in the back of a very old refrigerator. The naked mole rat. Heterocephalus glaber, roughly the size of a mouse. A mouse lives 2 to 3 years. A naked mole rat lives over 28 years, 9 times longer than a mouse of similar body mass. 9 times. That alone would make it one of the most studied animals in gerontology. But the lifespan is not the point. The point is what happens to its mortality rate as it ages. In 2018, Rochelle Boffenstein and colleagues at Calico Labs, a longevity research company funded by Google, published a study in the journal eLife. They had tracked over 3,000 individual naked mole rats across more than 30 years of observation in controlled laboratory colonies. They measured mortality rates at every age, and what they found broke one of the oldest and most robust empirical laws in all of biology. The naked mole rat does not show any increase in mortality rate with age. None. Zero. The Gompertz Law, which applies to every other mammal ever studied, from mice to elephants to whales to humans, simply does not apply. The hazard function is flat. A 25-year-old naked mole rat is no more likely to die in a given year than a 1-year-old naked mole rat. That is not a slight flattening of the curve at extreme ages. That is a fundamental violation of the pattern that governs every other mammalian species ever measured. They also show what the biogerontologist Caleb Finch calls negligible senescence. Finch coined the term to describe organisms that meet 3 strict criteria: no measurable increase in mortality rate with age, no measurable decline in physiological function, and no measurable decline in reproductive capability. The naked mole rat meets all 3. Breeding females show no decline in fertility even well into their 3rd decade of life. The animals maintain their body composition, their cardiovascular function, their bone density from age 2 to age 24 with only minimal changes, and they almost never develop spontaneous cancer. In over 3 decades of observation across thousands of animals, spontaneous neoplasms are essentially absent. And when you look at the molecular details, you begin to see how they do it. Their cells produce an unusually high molecular weight version of hyaluronic acid, a sugar polymer that fills the spaces between cells. The mole rat version is roughly 5 times larger than the human version, and it appears to prevent cells from crowding together too tightly, which is one of the early steps in tumor formation. Their proteins are more resistant to unfolding under oxidative stress. Their proteasomes, the molecular machines that break down damaged proteins, remain active at ages where mouse proteasomes have long since declined. They are not running different physics. They are running more accurate maintenance. The Gompertz exponent for the naked mole rat is effectively 0, and the mole rat is made of the same atoms you are made of: carbon, hydrogen, oxygen, nitrogen, phosphorus, sulfur, the same elements in the same periodic table. The same quantum mechanics governs its electrons. The same electromagnetic forces hold its molecules together. The same thermodynamics applies to every chemical reaction in its body. The same second law, with the same qualifier about closed systems, operates identically in a mole rat as in a human. Yet the mole rat does not age in any measurable way. The physics is identical. The engineering is different. And that raises a question, maybe the most important question in this entire discussion. Is aging a wall? Something built into the laws of physics that no amount of engineering will ever breach? Or is it a gap, a distance between what the physics permits and what biology has so far delivered? Hold that question. We will come back to it. A mouse and a mole rat are made of the same physics. One ages, one does not. The difference is not in the atoms, it is in the instructions. So what is different about the instructions? Why does the mouse age and the mole rat not? The answer is not in physics, it is in evolution. Evolution does not optimize for immortality. It optimizes for reproductive success. And these are fundamentally different objectives with fundamentally different engineering requirements. Think about it from evolution's cold arithmetic. If you are a creature in the wild, what matters for passing on your genes is surviving long enough to reproduce, and in some species, raising your offspring to independence. Once you have done that, from evolution's indifferent bookkeeping, you are expendable. There is no selective pressure to keep you running to 200 years old. There is no genetic reward for reaching 500. In fact, mutations that cause damage late in life, damage that only manifests after reproduction, are essentially invisible to natural selection. Their carriers have already reproduced and passed on those mutations before the damage ever appears. Natural selection cannot see them, cannot remove them. They accumulate silently across generations, and their effects only become visible long after the evolutionary ledger has closed. This is the disposable soma theory, proposed by Tom Kirkwood in 1977. Kirkwood recognized that every organism has a finite energy budget, and that budget must be divided between two competing demands: reproduction and self-repair. Evolution, operating through natural selection, consistently favors reproduction. The body, the soma, is disposable. It is a vehicle for the germline. Once reproduction is complete, the maintenance budget is no longer sufficient to prevent cumulative damage from overtaking the repair systems. You age not because physics demands it, but because evolution allocated your energy resources elsewhere. And the numbers bear this out. Your DNA repair systems are genuinely impressive. They correct roughly 10,000 to 100,000 molecular lesions per cell per day, 10,000 to 100,000 separate repair events in each of your roughly 37 trillion cells every single day. That is precision engineering on a scale that no human technology has ever approached. But the systems are not perfect. They miss errors. They leave damage unrepaired. And over decades, across tens of trillions of cell divisions, those errors accumulate. Your telomeres, the protective sequences of repetitive DNA at the ends of your chromosomes, shorten with each cell division. Roughly 50 to 200 base pairs are lost with every replication cycle. They function as a kind of molecular countdown timer, and they are not replenished in most of your somatic cells. When they reach a critical length, the cell receives a signal to stop dividing permanently and enters a state called senescence. The cell is alive, but functionally retired. It no longer replicates, and it begins secreting a cocktail of inflammatory signals called the senescence-associated secretory phenotype that damages the surrounding tissue and promotes chronic inflammation. This is the Hayflick limit, named for Leonard Hayflick, who discovered in 1961 that human cells in culture can only divide a finite number of times, roughly 40 to 60 divisions, before they stop permanently. Reactive oxygen species, chemically aggressive molecular fragments produced as an unavoidable byproduct of mitochondrial energy generation, damage proteins, lipid membranes, and DNA with every breath you take. Your antioxidant defense systems, including catalase, superoxide dismutase, and the glutathione system, neutralize most of them. But not all. The gap between damage and repair is small on any given day. Over decades, it compounds. And the compound interest on molecular damage is the Gompertz curve. Right now, your repair systems are correcting thousands of errors per second. They are winning. They have been winning every day of your entire life. They are just not winning by quite enough. And none of this, not one piece of it, is required by the laws of physics. All of it is a consequence of how the biological machinery happens to have been built by an optimization process that stopped caring once you reproduced. The Gompertz exponent is not a physical constant. It is an engineering parameter. It varies between species. It is 0.085 in humans. It is effectively zero in the naked mole rat. And the mole rat is not alone. Because here is the thing. If only one species had solved this, You could call it a fluke, a lucky mutation, a one-off biological curiosity with no broader implications. But it is not one species. Turritopsis dohornii is a jellyfish roughly 4.5 millimeters across, smaller than your fingernail. When it is stressed or injured or old, it does not die. It reverts. It transforms its specialized adult cells back into unspecialized juvenile cells through a process called transdifferentiation, the direct conversion of one differentiated cell type into another without passing through a stem cell intermediate. It literally resets its biological clock back to zero. Then it matures again, grows tentacles again, becomes an adult again, and then, if conditions demand it, it reverts again. As far as biologists can determine, this cycle can repeat indefinitely. The mechanism was first observed accidentally in the 1990s by students keeping specimens in a laboratory jar. In 2022, a team led by researchers at the University of Oviedo sequenced the genome of Turritopsis dohornii alongside a closely related non-immortal species and published a comparison in the Proceedings of the National Academy of Sciences. They identified the key molecular differences, amplified genes for DNA replication and repair, enhanced telomere maintenance pathways, expanded stem cell renewal programs. A completely different molecular toolkit than the one the naked mole rat uses. Same result. The Ru-Hai rockfish, Sebastes aleutianus, lives in deep cold waters from Japan to the Aleutian Islands at depths of 150 to 450 meters. Its confirmed maximum lifespan is over 205 years. In 2021, a team led by Peter Sudmant at UC Berkeley sequenced the complete genomes of 88 different rockfish species, some that lived barely a decade, some that lived 2 centuries, and published the results in Science. They found 137 genes associated with extreme longevity. The longest-lived species showed positive selection specifically in genes governing DNA double-strand break repair, better molecular proofreading, more accurate error correction, running on the same physics as every other fish in the ocean, just with more precise maintenance machinery. The bristlecone pine, Pinus longaiva, the Methuselah tree in California's White Mountains, has a verified age of 4,857 years. It germinated around 2800 BC. It was already centuries old when the Egyptians built the Great Pyramid at Giza. Before Stonehenge was completed, before the invention of writing, before the founding of Rome by roughly 2,000 years. It is still alive, still photosynthesizing, still growing new wood. And Hydra vulgaris, a tiny freshwater polyp, barely a centimeter long, whose stem cells maintain their regenerative capacity indefinitely under laboratory conditions. Researchers have monitored Hydra populations for years and found no detectable increase in mortality rate with age and no decline in reproductive output. The repair rate matches the damage rate, and the biological clock simply does not advance. 5 lineages, 5 completely different biological architectures: jellyfish, mammal, fish, tree, polyp. Separated by hundreds of millions of years of evolution, each arrived at its solution to the aging problem independently. Each uses entirely different molecular mechanisms. The physics in every case is identical. What varies is the engineering. Nature solved this problem at least 5 times, independently using 5 different strategies. That is not a fluke. That is a proof of concept. Now strip away all the biology for a moment. Ask just the physics. What does a self-maintaining open system need to persist indefinitely? 3 things. Energy. And the sun delivers to Earth in 1 hour more energy than all of human civilization uses in an entire year. Raw materials. And your body already replaces virtually every atom in its structure over a roughly 10-year cycle. You are not the same material you were a decade ago. And a repair mechanism that operates at least as fast and at least as accurately as the rate at which damage accumulates. Your repair systems currently run at roughly 95% fidelity. That is extraordinary. That is also the exact margin by which you are dying. Energy is not the bottleneck. Materials are not the bottleneck. The bottleneck is the distance between 95% repair fidelity and 100, and that brings us back to the question, is that distance a wall or is it a gap? In 1944, a man named Erwin Schrödinger, who had already won the Nobel Prize in Physics 11 years earlier for his wave equation, one of the foundational results of quantum mechanics, published a small book called What is Life? It became one of the most influential scientific books of the 20th century. James Watson, who would go on to co-discover the structure of DNA, read it as a 17-year-old undergraduate at the University of Chicago and later said it redirected his entire career toward understanding the gene. Francis Crick cited it as a major influence. An entire generation of molecular biologists traced their inspiration to a quantum physicist asking a single question that crossed the boundary between physics and life. The phrase everyone remembers from that book is negative entropy. Schrödinger argued that living organisms maintain their highly ordered state by feeding on negative entropy, by importing order from their environment in the form of food and sunlight and exporting disorder in the form of heat and waste. He later acknowledged, in a footnote added after publication, that the more precise term would have been free energy rather than negative entropy. The physicists who reviewed the book were right to push back on his terminology. But even the corrected version undersells what Schrödinger actually saw. You see, Schrödinger's deeper insight was not just about energy balance. It was about information. A living organism does not merely import calories and export heat. It imports structured molecular order, the specific spatial arrangements of atoms in food molecules, the low entropy photons arriving from the sun, and uses that structured order to maintain and continuously update its own internal pattern. A living cell does not just passively resist decay, it actively reads instructions encoded in its DNA. It detects errors in those instructions and corrects them. It responds to signals from neighboring cells and rewrites its own gene expression in response to changing conditions. That is not just thermodynamics, that is information processing, computation, running on thermodynamic machinery. And this is where Ilya Prigogine enters the story. In 1977, Prigogine won the Nobel Prize in Chemistry for a body of work that extended Schrödinger's insight into something much larger. Schrödinger had shown that open systems can maintain order by importing free energy. Prigogine showed something more radical, that systems driven far from thermodynamic equilibrium can spontaneously increase in complexity. Not just maintain their existing order, but generate entirely new order, new structure, new capability, new organization emerging from the sustained flow of energy through the system. He called these dissipative structures systems that create and sustain internal order by continuously consuming energy and dissipating entropy into their surroundings. A hurricane is a dissipative structure. A candle flame is a dissipative structure. A convection cell forming in a heated fluid is a dissipative structure. And so is every living thing on this planet. But living things do something that hurricanes and candle flames do not. They improve. Your immune system is a dissipative structure that increases its own complexity over time. It learns. When you encounter a pathogen for the first time, your B cells undergo a process called somatic hypermutation. They randomly mutate the genes encoding their antibodies at a rate roughly 1,000,000 times higher than the normal background mutation rate, and then selection within your own body. A miniature Darwinian process running inside your lymph nodes selects the variants that bind most tightly to the invader. The survivors become memory. B cells that encode precise molecular information about past threats and improve your response accuracy with each subsequent encounter. That is not maintenance. That is not holding steady against decay. That is a physical system using thermodynamic energy to generate new, more complex, more accurate internal structure. Self-improvement running on physics. And the lineage of life on this planet has been doing exactly this for roughly 4 billion years. Individual organisms die. The cellular machinery does not. It has been continuously operating, replicating DNA, synthesizing proteins, running metabolic cycles. without a single interruption across a span of time so vast that it defeats intuition. And it has not merely persisted, it has become more complex. Single cells became colonies. Colonies became multicellular organisms. Simple metabolisms became elaborate biochemical networks. Nervous systems emerged, then brains, then awareness. The information content of the biosphere has increased enormously over 4 billion years, all while the total entropy of the universe has also increased. Both statements are true simultaneously. The second law is not violated, it is satisfied, and within its constraints, complexity has grown and grown and grown. The loophole that Schrödinger identified in 1944 has never been closed. Nothing in physics will ever close it, and it is wider than he knew. It does not just permit maintenance, it permits growth. So let me return to the question. A wall is a physical law you cannot cross. The speed of light, the conservation of energy, the uncertainty principle, the absolute zero of temperature. These are walls. They are woven into the mathematical structure of reality itself. No amount of engineering, no amount of ingenuity, no amount of centuries of sustained effort will breach them. They are not challenges to be overcome. They are boundaries. A gap is something else entirely. A gap is insufficient knowledge, insufficient capability, insufficient precision. A gap is the distance between what the physics permits and what the engineering can currently deliver. And gaps close, walls do not. Is the distance between the human Gompertz exponent and the naked mole rat's flat mortality curve a wall or a gap? The physics is clear. No law of thermodynamics requires a self-repairing open system to fail. The Gompertz exponent is not a physical constant. It varies between species and reaches zero in at least one mammal. 5 separate lineages, spanning the full breadth of multicellular life, have independently evolved negligible senescence using 5 entirely different molecular strategies. Dissipative structures driven far from equilibrium can not only maintain their complexity but spontaneously increase it. The open system loophole has been operating for 4 billion years and has never once closed. There is no equation in physics that says you must age. There is no theorem that proves a sufficiently precise repair system must eventually fall behind. There is no law written into the structure of the universe that draws a line at 70 or 80 or 120 and says, here. No further. The equations are silent on the subject. They do not care how long you last. Gravity does not check your age. The electromagnetic force does not read your telomeres. The atoms in a newborn and the atoms in an elderly person obey precisely the same laws. The difference is entirely in the arrangement, the pattern, the information, the engineering. Aging is a gap, possibly a very large gap, possibly a gap that takes centuries of sustained scientific work to close, but a gap, not a wall. Walls are made of physical laws, gaps are made of physical laws, gaps are made of ignorance, and ignorance is temporary. The Gompertz exponent for humans is 0.085. For the naked mole rat, it is 0. The distance between those two numbers is not a law of physics. It is a measure of what we have not yet learned to build.